We are now going to part B of lecture 2, and we reached to page 7. And if you go to figure 2 with me, figure 2, which is a sample of how to plot a graph. You have to put the x-axis first and then the y-axis. And for example, if you have activity on the y-axis, you have to put activity. Of course, you number it because there are linear and there are other curves which is logarithmic. So this is linear. This curve is linear. Okay, so when you put the activity, you have to put between brackets, put the units. That is essential in any curve. When you plot a curve, that is essential. So what is the units for the activity? Curie. We symbolize Curie by CI, Curie. Okay, the activity is Curie. That is because of the name of Madame Marie Curie. She's a French scientist who discovered radium. And because of that discovery, in the early times of radiation, they gave the units of activity to her name, Curie. Now that's the y-axis. In the x-axis, again, you make the divisions equal. If it is linear curve, if it is a logarithmic, that's different case. And it is processing time. Again, between brackets, put the units. The units are minutes. And then you put your points. You might ask me about these error bars. These are error bars. The points are triangles, and every triangle there is error bar. Error bar, that is the error of every reading. Okay, so now we go to the sample problem 3, and he is telling you how to find out x. If you have x cubed equal 2.67, what will be the value of x? Grab your calculator and do that, and try to do it yourself before you look at the answer. Okay, that's a good exercise for you. And another exercise, x equal to the minus 2.71, the root 2.71, remember, and the root is 1.5 times 10 to the minus 3. So do that again yourself and then look at the answer. These are simple stuff. Okay, now we go to page 8. Page 8, if you have exponential function like the one is in sample problem 4, if e to the x equal to 13, what's the value of x? You take ln of both sides. So when you take the ln of e to the x, it will be x itself. When you take the ln, the natural logarithm of e to the x, it will be x. Now ln of that equal to ln of 13. Ln of 13, you take it from the calculator, okay, and that will be the value of x. And if the exponential is negative, example 2, same thing. Okay, now we go to page 9. There is figure 3, which tells you the definition of the trigonometric functions. Sine alpha is the opposite over the hypotenuse, and adjacent to the hypotenuse is the cosine, tangent, opposite. You know this from your mathematics. I don't think this is very difficult to, I think everyone should know it by heart, by the way. This is no. And he is now giving you an example in problem sample problem 5, and he said find the unknown variable y if you have 10y equals 6.823 tangent 14 over sine 81. So you have to go to the calculator and make tangent, find out tangent 14, which is 0.249. Find out sine 81, which is 0.988. And make sure when you say sine, you have to make you have to adjust your calculator to put degrees, because sometimes they put it in radians, so you have to put degrees. Okay, and then you could find out this. Again, try to do the solution yourself and then check it with the book. Basic Physics Review, page 9, Structure of Matter. Okay, what is the structure of matter? Matter consists of atoms, and the atom consists of electrons revolving around the nucleus, and in the nucleus there are protons and neutrons. Okay, so this is the structure of the atom. Okay, now there is an error in this page. Make a correction with the pencil. Instead of figure 3 in line 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20, 28, line 28 from top, there is figure 3. It should be figure 4, not figure 3. That's an error. I will send a letter to Golnick about it. Okay. Now, I told you that inside the atom there is a nucleus, and around the nucleus there are electrons rotating. Now, what are the neutrons make of? Neutrons make of elements called quarks. Okay, and here in the figure 4, he is telling you that every quark has up and down, and all these. Every one of them has a special charge and special energy. These are the constituents of the neutrons and protons. Okay, quarks. It's called quarks. Okay, and that is the microscopic scale of structure of matter. Now we come to page 11. Page 11, there is the Newtonian mechanics. Newton, in the 17th century, discovered 3 laws. The first one is the law that say that the force is equal to the mass times acceleration. Okay, and he defined that the acceleration is the rate of change of the velocity. Okay, so now the energy is, he defined the definition of energy is the rate of doing work. That's the power, the rate of doing work. The work is force times distance. The potential energy is the mass times height times the acceleration of the gravity. Okay? And in sample problem 6, he is giving you an example of, and the power, of course, is the work, the rate of doing work, and the units of power is, in our units, horsepower. In their units, in the SI units, they use joule. Oh, sorry, watt. Joule is the energy. For energy, they use joule. For the power, they use watt. Watt and megawatt for 10 to the 6 watt. Okay? Now, there is an example which is interesting here. How fast can the block be raised how long would it take, and so on. So the power is work per unit time. He changed the horsepower into foot-pound. Every horsepower is equal to 550 foot-pound per second. Okay? So if you divide that by 1,000, because he said 1,000, the mass is 1,000 pound. So if you divide that by 1,000, that means you get the velocity, 0.55 feet per second. Okay? So to lift this 20 feet, you have to divide the 20 feet by the velocity to get the time. Okay? And if you want the engine, instead of the engine rated, the power of the engine, which is, we said it is 1 horsepower, if you want to make it into the SI units, you have to convert it into joule per second, which is watt actually. He did not say watt, but you could make in pencil, you will say watt. Here, W. Symbol of watt, W. So 746 joule per second, which is watt, W. Okay, now I want you to pay attention to the temperatures. We use this absolute scale for the temperature. For this degree centigrade, you add 273. So if you have a temperature in degree centigrade and I ask you, what is the temperature in absolute units? You add 273 to it. So if the temperature is 20 plus 273, it will be 293. And the units for the absolute is Kelvin. K, Kelvin. Is it written here? Kelvin, yes. So if you go to figure 6, the second column, Kelvin. That is the units of the SI system. And Celsius is the temperature. And this is the Kelvin absolute. Celsius is not absolute. In our case, you have to add 460. What's that? 459.67. It is 460 anyway. It is 460. We add 460 to our degrees to get it in absolute units. So if your temperature is 40 degree Fahrenheit, I ask you, what is the absolute temperature, please? 460 plus 40, it will be 500 degree Rankine. We say for the absolute units in our system, degree Rankine. Okay? And so you have now two things in the absolute units. Kelvin for the SI units and Rankine in our units. Okay? That is as regard as the what's called that? Chapter physics, Newtonian mechanics. Now we go to electricity. In page 13, bottom of the page, electricity, and he is explaining to you the electricity in simple terms. The first explanation is the Coulomb law. So if you have a charge that is, say so and so Coulomb, and the other charge is either positive or negative, so and so Coulomb, the force between these charges, it will be repulsive if the charge are similar. It will be attractive if the charge are different. So the law that governs that to get the force is K Q1 Q2 over R square. R is the distance, separation distance between the charges, and K is a constant. That's Coulomb law. Okay, and here in sample problem 7, he is showing you how to calculate this force. Okay, he is showing you how to calculate this force. Okay. Okay, so now we go to this sample problem, and he gave you two charges separated by 1.4 millimeter, and the charges are 13 Coulomb each. One negative and the other is positive. So the force will be attractive in this case. Okay. So he applies the law F equal K Q1 Q2 over R square, and K, he did not put the value of K, and he made the result in terms of K anyway. And he changed the 225K. The new force will be about 2.6 times stronger and still attractive because they are different. These charges are different, one positive and one negative. That's why the force is attractive. Now there is in page 15, I beg your pardon, page 15, you have page 15, you have the basic law of electricity. The voltage is equal to the current times the resistance. V equal IR, or I equal V over R, or R equal V over I, that's the same thing. And V is the potential difference in volts, and I in current in ampere, and R is the resistance in ohm. Okay? Now if you want the power simply is I times V. I times V. That's the power. Okay? And here is an example. He gave you sample problem 8. A 12-volt automobile lamp has a rating of 30 watt. The bulb resistance, find the bulb resistance and the current. So we have the power is IV, or V times I. So I will be W over V. So 30 watt divided by 12, so the current is 2.5 ampere. What else you want? You want you to get the resistance. The resistance is V over I. You already got V 12 volt, and you already calculated the current 2.5. Divide those two, 4.8 ohm is the resistance. Now, in electricity, we have two systems, AC and DC. AC is the current that moves in non-periodic, non-repeating waves, constant waves in one direction. In the AC, the wave is sinusoidal. Now, there is a wavelength. Always there is a wavelength. Whenever you have a wave like that, there is a wavelength. And if you want to get the wavelength, it will be the velocity of light divided by the frequency. Okay? The velocity of light in vacuum is 3 times 10 to the 8 meter per second, or 3 times 10 to the 10 centimeter per second. That's the velocity of light. Now, in electricity, we have two types of connections in the circuits. You either make the connection series, like in figure 10, or in parallel. Okay? And I'm pretty sure you know these things from your course of electricity with Dr. Tisseroni, Mr. Tisseroni. Okay, so now we go to page 18, and there is a problem there also in a series circuit containing inductance. Now, if you have AC circuit, instead of resistance, you will have inductance. Okay, and you have to go through the equations to get the values for this parameter. Okay, and three-phase, if you have three-phase, also you go through this and read about the three-phase and how do we do this in the communications and in the transportation. Now, in the page 20, the electronics. He started from the page figure 12. These are the old types of electronics. Nobody is using these things anymore. These are called vacuum tubes. and you could use them to change from AC to DC. You could use them for amplification, amplifiers, and so on. Nobody is using these things anymore. People now use semiconductors on page 22, semiconductors, or integrated circuits in figure 14. These are the most modern type of electronics we employ nowadays. Now, page 22, biology. Page 22, he's talking about biology now, and the major organ system of the body are, first of all, the